They
Congratulations,
celebrated too
comrade. A
early.
job well done.
When
Thank
the
you,
wooden
Colonel.
crate
It was a
arrived at
difficult
Lubyanka's
operation, but worth
technical
it.
directorate in late 1959, the officers of the KGB's Line X division gathered around it like victorious hunters. Inside lay what they believed to be the crown jewel of Cold War espionage. A fully photographed and microfilmed set of American blueprints for a next-generation integrated weapons control system. A device so modular, so precise, and so far ahead of Soviet equivalents that Moscow believed it could erase a decade of technological lag in a single stroke. Colonel Victor Markin, the directorate's lead analyst for Western technology, flipped through the microfilm reels and smirked. "Typical Americans," he muttered to his aides. "They hide their weaknesses under mountains of steel and mass production. Brute force instead of brains." His assistants laughed. The Americans, in their view, were industrial peasants with machine tools, nothing more. Engineering elegance, they insisted, belonged to the USSR. For a moment the room buzzed with triumph. The logic was intoxicating. If the CIA steals secrets, it earns headlines. But when the KGB steals secrets, it erases American advantages before Washington even knows they existed. And this time, they believed, the coup was historic. The system they thought they had captured, part computer, part sensor nexus, part electronic brain, was the heart of a new U.S. weapons platform that NATO planners whispered about in tones of unease. If the USSR could copy it, parity was within reach. A junior engineer threaded the first reel through a magnifying viewer. The schematics appeared sharp, layered, meticulously labeled. Power distribution grids, cooling arrays, circuit boards denser than anything Soviet factories could reliably produce. He exhaled in awe but quickly masked it, muttering, "Nothing extraordinary, over-engineered, wasteful." Markin nodded. Americans compensate for their lack of precision with abundance. Give them enough metal, enough subcontractors, enough electricity, and they think they've achieved sophistication. The laughter returned, nervous this time, though no one yet understood why. The room's brightest men stood before a crystalline image of American engineering and saw only hardware. They believed the West had handed them the keys to its most guarded technological vault. A blueprint, after all, was supposed to be the ultimate truth, and Soviet doctrine had long convinced them that once the dimensions were known, the machine could be built. What none of them considered, not in those first moments, not even as they bragged to their superiors, was the single fatal assumption that would unravel the entire operation: that a blueprint is a machine. It was not. The Americans had built a system, not a device, an ecosystem, not a component. And the men in that crowded room, drunk on victory, could not yet grasp that what they held in their hands was nothing more than a shadow of something far larger, far more intricate, and utterly beyond the reach of Soviet industry. For now, they smiled. But soon those smiles would dissolve into the quiet horror of realization. The Soviet confidence was not arrogance born overnight. It was the inevitable product of a system that had convinced itself that scarcity was a virtue. Within the USSR's industrial and scientific circles, the belief had hardened into doctrine. When resources are limited, engineers become sharper, solutions become elegant, and machines become lean, efficient, and superior. American abundance, mountains of aluminum, oceans of oil, endless rows of automated mills, was viewed not as an advantage but as a kind of intellectual crutch. This mindset shaped everything: Soviet design bureaus prided themselves on minimalism. Fewer parts, fewer machining steps, fewer alloys, fewer failure points. If a component could be cast instead of milled, they cast it. If a circuit could be simplified, they simplified it, even if performance suffered. In that world, the American approach, with its obsession for redundant wiring, precision machine tolerances, modular subsystems, and layered quality checks, was interpreted as evidence of laziness rather than discipline. Thus, when Soviet intelligence recovered the American blueprints, the KGB's analysts filtered them through the logic they had inherited. They interpreted complexity as bloat. They viewed the extensive parts lists as inefficient. They skimmed through the meticulously cross-referenced manufacturing notes, each referencing subcontractors, tolerances, statistical control charts, and saw them not as essential instructions but as bureaucratic clutter. The confidence also came from precedent. The USSR had copied Western systems before, and sometimes with remarkable speed. The 2-4 Bull, a reverse-engineered B-29, was the crown jewel of that legacy. To Soviet planners, it proved that any Western machine, no matter how complex, could be reconstructed with sufficient manpower and central planning. They conveniently forgot that the Tu-4 project required over 900 factories, multiple emergency reallocations of national resources, and a level of political terror so suffocating that entire teams of engineers lived in fear that a mismachined bracket could send them to a gulag. They remembered the success, not the cost. That selective memory fed their assumption. The Americans built machines, the Soviets built solutions. The West was obsessed with consumer-grade perfection, the East with military necessity. What mattered was function, not elegance. And if an American system worked, the Soviet version, produced with fewer materials and fewer steps, should work too. This thinking was reinforced by their command economy worldview. Soviet planners believed that centralization created efficiency. One ministry controlled metals, another controlled electronics, another controlled transport. So long as Moscow issued the order, the factories would align. They did not understand that American industry thrived not because it was centralized, but because it was decentralized, because thousands of independent firms competed to meet the same standard, driving quality upward through constant iteration. The final and most damaging source of Soviet confidence was their misunderstanding of American technological culture. Soviet engineers were excellent, often brilliant, but they worked in an environment where improvisation was a necessity because consistency was impossible. Machine tools varied, alloys varied, voltages fluctuated, components warped. Nothing was identical from batch to batch. When they looked at American blueprints, they saw what they were accustomed to. Hardware defined by clever engineering compensating for national scarcity. They could not yet imagine a nation where every bolt, every transistor, every machined edge was identical because the system made it so, predictably, repeatably, relentlessly. Thus, as they studied the stolen American blueprints, the men of the KGB and the Soviet design bureaus did not realize their foundational mistake. They were looking at the end product of an industrial civilization whose underlying infrastructure they had never experienced, never conceived, and fundamentally misunderstood. The first signs of trouble appeared quietly. So quietly that no one in the KGB's technical directorate wanted to acknowledge them. A young metallurgist reviewing the American stress diagrams noticed something unsettling. The tolerances specified in the blueprint were so tight that several Soviet factories would need to recalibrate their machine tools by an order of magnitude just to begin fabrication. He hesitated to say it aloud. In the Soviet system, pointing out an impossibility was often more dangerous than attempting it. But the deeper the specialists dug into the schematics, the more they realized the same truth. The Americans had not built a device, they had built a culture of precision. The invisible advantage of the United States, so invisible that the Soviets had never learned to look for it, was the industrial ecosystem wrapped around every blueprint. When an American engineer designed a module requiring a 0.005-inch machining tolerance, he did so knowing that a supplier in Illinois, another in Ohio, and 3 more in California could all meet that requirement on demand at scale and with repeatable reliability. When he specified a particular aluminum alloy, say 7075T6, he took for granted that refineries across the country could produce it to exact composition, identical from batch to batch, because the entire supply chain followed shared national standards. None of this appeared in the stolen blueprints. The Americans didn't need to annotate, "This transistor works because we have 14 independent manufacturers that produce millions of them per month, all within 0.1% performance variance." They didn't need to footnote, "This cooling system only functions because U.S. metallurgy produces heat-treated components with uniform crystalline structures." They didn't need to add warnings, "Do not attempt to build this unless you have a national network of suppliers using the same tolerancing culture, statistical quality control, and industrial feedback loops." To them, these were environmental assumptions, like oxygen, so fundamental that they didn't need to be spoken. For the Soviets, they were missing pages in a sacred text. Line X analysts were especially confused by the American notations on quality control. They found layers of redundant testing, component inspections, subsystem verifications, environmental stress screening, automated diagnostic routines. The mindset behind these steps baffled them. In the USSR, inspections were often political rituals. Errors were hidden, not corrected. Quality issues were often solved by rewriting reports rather than re-engineering processes. The American practice of measuring failure rates, quantifying defects, and feeding that data back into manufacturing struck Soviet engineers as wasteful, even neurotic. They did not understand the purpose because they had never lived inside a system where quality was not episodic but structural. Then there was the modularity. The stolen system was built out of standardized components that could be swapped like building blocks, each designed by different companies yet perfectly interoperable. To Soviet analysts, this was madness. They were accustomed to vertically integrated factories producing entire systems under a single roof, where compatibility was enforced through proximity, not standards. They did not grasp that American modularity was not chaos. It was choreography. A Midwestern machine shop could produce a guidance component knowing it would mate flawlessly with an avionics module from Texas, which would integrate perfectly with a power unit from Connecticut. This required not only engineering discipline, but an entire nation aligned around industrial interoperability. The final revelation, the one that truly shook the first wave of analysts, came when they examined the statistical process control graphs built into the blueprint appendices. Each curve, each deviation band, each tolerance window told a story of factories that constantly monitored themselves, adjusted themselves, and optimized themselves without waiting for orders from above. Where Soviet plants ran on quotas, American plants ran on data. Only then did the first whisper of dread move through the team. The Americans hadn't beaten them with superior engineering brilliance. They had beaten them with an invisible architecture surrounding the blueprint, an industrial ecosystem scaling across half a continent, powered by competition, standardization, and precision culture. The USSR could steal the technical drawing, but the Americans had built the real secret into the very structure of their economy. The Soviets had obtained the recipe, but they did not possess the kitchen, the tools, the ingredients, or the chefs. The stolen system was not some peripheral gadget. It was the core of an American weapons revolution. In the mid-Cold War, the U.S. had begun deploying a new generation of integrated fire control computers for high-altitude interceptor aircraft and long-range air defense batteries. Unlike previous analog machines, these hybrids fused early solid-state electronics, inertial sensors, and modular logic units into a single synchronized brain capable of processing targeting data in milliseconds. To NATO planners, it was the first glimpse of a future where speed of computation, not merely engine thrust or missile range, determined who controlled the sky. To Soviet air defense strategists, already alarmed by America's expanding bomber fleet and rapidly advancing radar networks, it was a technological threat that demanded immediate parity. The specific system at the heart of the KGB coup was the ANASQ-26 derivative, a modular American guidance and fire control suite designed to coordinate radar input, compute ballistic solutions, stabilize targeting platforms, and interface with missile systems. In testing, American crews reported reaction times up to 40% faster than previous systems, and accuracy improvements so significant that Pentagon analysts quietly revised projected kill probabilities for both intercept missions and defensive counter-air operations. Worse for Moscow, the Americans were not producing these units by the dozen. They were preparing to produce them by the thousands. The U.S. Air Force had already mapped integration pathways into several aircraft types, from interceptors to strategic bombers. Meanwhile, major defense contractors had begun tooling up their subcontractor chains. Transistor foundries, alloy mills, printed circuit manufacturers, micro-relays, gyroscopic components, thermal regulators, and shock-mounted housings. A single American fire control unit might depend on hundreds of firms across the nation, each capable of high-volume, high-consistency output. For the Soviet Union, which struggled to maintain even small-batch electronics production with acceptable reliability, the strategic implications were terrifying. This was why the GRU and KGB launched a coordinated espionage campaign to extract the design. The Politburo believed that if they could replicate the American guidance suite, even in reduced form, they could stabilize their vulnerable air defense network and close the widening gap in reaction time. The logic seemed sound. Steal the blueprint, build the machine, deploy the system, negate the American advantage. Inside the Kremlin's military-industrial committees, the optimism bordered on euphoria. If they could copy the unit, they could retrofit it into upcoming interceptor projects. They could mount it on air defense batteries defending Moscow. They could even adapt its computational core for ballistic missile defense concepts, still in early study phases. The leadership spoke as if parity were a foregone conclusion. Soviet engineers shared that optimism initially. On paper, the system looked both brilliant and replicable. It was compact, modular, elegantly divided into swappable functional blocks. It used American standardized connectors that seemed simple enough to replace with Soviet equivalents. The microfilm reels revealed no exotic physics, no secret materials unavailable east of the Iron Curtain. It looked like something the USSR should be able to produce. That assessment held until they tried to build the first subsystem. The moment fabrication began, triumph turned to confusion, then to frustration, and finally into something close to panic. The Americans hadn't built a device. They had built an industrial symphony, and the Soviets had only managed to steal the sheet music, not the orchestra. The first fabrication reports reached Moscow in thin, nervous packets, carefully worded, cautiously optimistic, and utterly misleading. Managers at plant number 14 in Novosibirsk claimed they could machine the structural housing of the fire control unit with minor deviations. Those deviations, when examined by central inspectors, exceeded American tolerances by factors of 10 to 40. A bracket specified at plus 0.05 inches arrived at plus 0.02. A gyro housing that required perfect symmetry drifted so far off axis that its rotational error made the entire module unusable at anything above taxiing vibrations. The numbers told the story long before any engineer dared speak it aloud. Where an American subcontractor could hold plus 0.03 across a run of 10,000 parts, Soviet plants struggled to hold plus 0.005 on a run of 50. What the USSR blamed at first on initial adaptation issues soon revealed itself as a systemic, immovable barrier. Not a single Soviet facility could meet the tolerances required for the precision bearings inside the guidance computer. The United States used bearings from multiple competing firms, New Hampshire Ball Bearings, Timken, and others, each capable of producing exact replicas of the same part with defect rates under 0.3%. Soviet bearing plants operated with defect rates between 12% and 22% depending on material batch quality and machine tool wear. And that was only the beginning. The American system relied heavily on early-generation printed circuit boards manufactured with near-uniform copper thickness and consistent dielectric properties. The U.S. industry produced them at volumes exceeding 150,000 boards per month with variance so low that designers could assume perfect electrical behavior. When Soviet plants attempted the same process, conductivity varied by up to 15%. Copper adhesion failed after thermal cycling, and misalignment between layers produced logic errors the moment vibration exceeded mild thresholds. The data compiled by Soviet test teams was brutal. American PCBs passed vibration and heat stress tests 93% of the time. Soviet equivalents passed 17% of the time, and only when assembled by hand, individually tuned and tested outside normal production flow. Then came metallurgy. The Americans relied on alloys like 7075T6 and 6061T651, heat-treated and rolled with such consistency that mechanical properties varied less than 1% across entire shipments. U.S. rolling mills used automated temperature controls, infrared monitors, and chemical sampling protocols that produced identical batches year after year. The USSR tried to replicate this. The results resembled a parody of industrial science. One alloy batch cracked under machining. Another failed stress tests at half the expected load. A third batch showed grain structures so inconsistent that two pieces from the same ingot behaved like different metals entirely. Quality inspectors joked grimly that Soviet alloy consistency could be measured not in microns but in centimeters. Meanwhile, American production data, leaked through trade publications and intelligence intercepts, made the contrast psychologically devastating. Where the U.S. could machine 5,000 identical chassis per month across 5 states, the USSR could barely complete 40 prototypes, none of which met the required specifications. Where American production lines achieved uptime above 92%, Soviet lines averaged 63%, collapsing whenever a machine tool needed recalibration or a metallurgical batch failed. Where Americans could source transistors from a nationwide electronics industry capable of producing over 400 million units annually, Soviet plants produced barely 7 million, many of which exhibited catastrophic failure modes under heat or shock. The final blow came during thermal cycle testing. American units maintained logic integrity from 55 to 125 with failure rates under 1.1%. Soviet-built prototypes failed at plus 165. A temperature a fighter interceptor would exceed simply sitting on the tarmac in sunlight. Internal memos started circulating with unmistakable panic. A technical report from the NII-33 Electronics Institute summarized the disaster in one sentence that would later be quietly classified. "We cannot build the American device because we cannot build the America that builds the device." Senior party officials tried to hide the scale of failure, but numbers have an authority that ideology cannot bend. The Soviet light industrial sector lacked volume. The machine tool sector lacked precision. The metallurgical sector lacked purity. The electronics sector lacked reliability. And the quality control apparatus lacked any coherent mechanism for improvement. What they had stolen was the external skeleton of an American system powered by tens of thousands of companies, millions of workers, and industrial standards that stretched like arteries across the entire continent. By the time the Politburo realized it, it was too late. The blueprint had become a mirror, revealing not American secrets but Soviet limitations. The breaking point did not arrive with a dramatic explosion or a single failed test. It arrived with silence, long, heavy, career-threatening silence, in a conference room at the Ministry of Radio Industry in early 1962. Laid out on the polished table were the latest test logs for the Soviet-built replicas of the American fire control computer. Every subsystem had failed not once but repeatedly, and often in ways the engineers had no vocabulary to describe. The gyros drifted unpredictably. The transistor arrays overheated under loads far below their theoretical limits. The logic boards produced random oscillations whenever subjected to airframe vibration. A single shock event at 5G, 1/6 of what American units tolerated, scrambled the entire computational chain. The senior engineer, academician Sokolov, stared at the pages as if they were a personal insult. He had overseen reverse engineering projects for 2 decades. He had rebuilt German rockets, American radar sets, even components of the B-29. But this American system, refused to behave like anything he had encountered. "It is not a machine," he finally muttered. "It is an ecosystem pretending to be a machine." No one responded. They all understood, but none wished to be the first to voice the obvious. They had reached a wall that could not be climbed. The deeper they probed, the more humiliating the revelations became. The American designers had assumed uniformity so absolute that even the thickness of solder traces mattered. Soviet solder varied by composition depending on which regional plant produced it. American thermal pads relied on silicone compounds produced at precise viscosities. Soviet analogs separated into layers under heat. Even the rubber shock mounts, so trivial in appearance, were manufactured in the U.S. To chemical tolerances the Soviet rubber industry could not match. Every attempt at heroic engineering, the Soviet term for improvisation under pressure, only worsened the chaos. They redesigned housings to compensate for tolerance drift. They hand-trimmed PCB traces to stabilize logic flow. They substituted heavier, less efficient alloys for American composites. But each fix created new errors, and each new error amplified another. The Americans could drop a fire control unit into a factory line and expect it to work. The Soviets required custom adjustments on every single prototype, and even then most collapsed under performance testing. By late 1962, the atmosphere inside the design bureau had shifted from frustration to dread. A classified internal review from KB1 put the truth into unforgiving words. Replication is impossible without a corresponding replication of American industrial methodology, supply standardization, and statistical process discipline. We do not possess these. The psychological breaking point came when the KGB liaison to the project, Lieutenant Colonel Krutov, confronted the engineers. He demanded to know why progress had stopped, why deadlines had been missed, why the Politburo's expectations were being defied. Sokolov simply handed him the latest charts. Deviation bands collapsing, error rates exploding, thermal failures increasing with every iteration. Krutov scanned the pages in growing disbelief. When he looked up, the room saw something rare: fear. So the blueprints were incomplete? He asked. Sokolov shook his head. No, they were perfect. Then what is missing? The reply became legend within the closed world of Soviet military science. America. America is missing. The silence that followed was worse than shouting, because at last, even the party representatives understood. They were fighting not a machine, not a design, not even the CIA. They were fighting an industrial civilization built on precision principles the Soviet Union had never developed, and perhaps never could. From that point forward, no one spoke confidently of closing the gap. The engineers no longer believed parity was possible. The intelligence officers no longer believed blueprints were enough. The Politburo no longer spoke of replication, only of improvisation, degradation, and last-minute substitutions. The USSR had captured the form, but the essence remained locked behind a wall no spy could penetrate. When the failure could no longer be buried under rewritten reports or patriotic euphemisms, the Kremlin shifted to its default survival instinct: strategic improvisation. The original dream, an exact Soviet duplicate of the American fire control system, was quietly abandoned. What replaced it was a patchwork of compromises, downgrades, and emergency redesigns that exposed the widening technological gulf between the superpowers. The first consequence was operational. Soviet air defense regiments that were supposed to receive the new guidance suite instead received downgraded analog hybrids, systems that required triple the crew, produced half the accuracy, and suffered from reliability intervals measured not in hundreds of hours like the American units, but in tens, where the U.S. could field a squadron of interceptors with near-identical equipment. The USSR deployed machines that varied from aircraft to aircraft, each requiring individualized calibration and constant maintenance triage. This inconsistency didn't just degrade performance, it crippled doctrine. Soviet planners had hoped the new system would provide the reaction speed necessary to intercept high-altitude American bombers before they released standoff weapons. But even the best Soviet substitutes produced targeting solutions too slowly, too inconsistently, and with error margins far outside acceptable thresholds. The gap between American and Soviet interception capability, instead of closing, widened. Then came the cost. The improvised Soviet workaround consumed far more resources than the Politburo ever anticipated. Factories were reassigned, specialists were pulled from other projects. Electronics plants, already overstretched by missile program demands, were forced to retool for components with failure rates that made mass production almost meaningless. Every attempt to simplify the system increased complexity somewhere else. Every attempt to reduce tolerances caused new waves of defects. The Soviet state poured rubles into the effort and received instability in return. What made this especially tragic was that the Americans were scaling upward at the same time. By the early 1960s, U.S. defense contractors had refined their processes, automated their tooling, and expanded their subcontractor networks. Production volume rose, unit costs dropped, performance soared. New variants entered service with improved thermal resilience, upgraded transistor arrays, and faster computational cores. The American system was not a fixed target, it was a moving one, accelerating away with each production cycle. Internal Soviet assessments became increasingly bleak. A 1963 classified summary to the State Committee for Defense Technology concluded, "Our chosen path ensures permanent inferiority. We cannot match American improvements in frequency. We cannot match their component uniformity, and we cannot match their industrial tempo." The strategic implications were enormous. The Soviet Air Force had to adapt its entire defensive posture, relying more heavily on layered ground-based intercept systems and larger numbers of interceptor sorties to compensate for the slower reaction time. In effect, they replaced American precision with Soviet quantity, a costly exchange that strained logistics, manpower, and fuel reserves. Meanwhile, U.S. forces operated with such consistent reliability that they could reduce sortie load while increasing overall mission effectiveness. This mismatch did not merely shift tactical considerations, it reshaped the entire strategic landscape. Where the Soviet economy already labored under the weight of military expenditures approaching a third of national output, the United States spent proportionally less and received exponentially more capability. The USSR entered a technological debt spiral. Every American advance forced disproportionate Soviet investment just to maintain unstable equilibrium. The stolen blueprint intended to grant parity had instead revealed a structural asymmetry so severe that no level of espionage could overcome it. By the mid-1960s, Soviet leaders stopped asking whether they could catch up. They asked instead how long they could afford to keep pretending they might. The answer, whispered in classified chambers across Moscow, was not encouraging. In the years that followed, the failure of the fire control replication program became a quiet parable within Soviet scientific circles. A lesson whispered between engineers who understood that the true battlefield of the Cold War was not espionage. Not ideology, not even weapons themselves, but the industrial civilization that created them. The stolen blueprints, once celebrated as a masterstroke of KGB brilliance, were locked away in archives that no one visited anymore. They had become symbols of something far more painful than a failed technical project. They were evidence that the Soviet Union had misinterpreted the nature of American power. For decades, Soviet doctrine insisted that technology was an object, something concrete, discrete, stealable. But the Americans had built technology on top of infrastructure, infrastructure on top of industry, industry on top of standardization, and standardization on top of a national culture of precision and competition. It was a tower of capability whose foundations stretched far below what any blueprint could ever reveal. The United States had created an environment where a design could be mass-produced faithfully, effortlessly, continuously. The USSR created an environment where each machine was a small miracle of improvisation, and miracles by definition do not scale. This was the strategic legacy of the failed replication. The Soviets learned that some advantages cannot be stolen. They must be built, patiently, structurally, culturally, over generations. The realization forced Moscow to rethink its strategies. Where it could not compete with the United States in precision systems, it shifted to brute force alternatives. Missile barrages instead of guidance accuracy, redundant radars instead of sensor fusion, sheer quantity instead of reliability. It was the only approach the Soviet economy could sustain, and even then, just barely. But the lesson lingered, corrosive and unforgettable. In private, away from party officials and propagandists, Soviet engineers spoke with a mix of frustration and reluctant admiration. They knew the truth better than anyone. The blueprint had never been the treasure. The treasure was the system that made the blueprint real. One declassified line from a 1965 memo written by an anonymous member of the Military-Industrial Commission captured the tragedy with brutal clarity. We did not fail to copy the American machine. We failed to copy the American world. That was the final admission, the quiet punchline to a decade of technological humiliation. The KGB had stolen the shape of American power, but none of its substance. And in the long arc of the Cold War, this failure proved decisive. It was not the espionage victories, but the systemic defeats that shaped the century. The Americans could afford to innovate relentlessly because their industrial base made every innovation reproducible. The Soviets could only imitate selectively because their industrial base turned every imitation into a gamble. In the end, the greatest secret of the United States was the one the USSR could never smuggle, photograph, or decode, a civilization engineered for scale, precision, and acceleration. Against that, no intelligence service on Earth could prevail.
The moment Jesus' words faded, I felt a violent pull, like I was being ripped backward through a tunnel of light. The peace of his presence slipped from my grasp, and suddenly everything became heavy, loud, and unbearably physical. I gasped as air slammed back into my lungs. I was on my bedroom floor. My chest burned. My body shook. My heart pounded like it was restarting after being frozen in time. I heard myself groan, and for a moment, I wasn't sure if I was alive or still somewhere between worlds. The familiar smell of my room, the faint hum of the refrigerator down the hall, all of it hit me at once. I was back. I lay there for several minutes, unable to move, crying uncontrollably. not from fear, but from the overwhelming weight of what I had just experienced. I knew without a doubt. I had died. I had met Jesus, and he had sent me home with a mission. In the days and weeks that followed, everything changed. My priorities shifted. My heart softened. The noise that once drowned out God became quieter. I found myself longing for his presence, seeking him daily, choosing forgiveness, reconnecting with community, listening for his voice. And above all, I knew I couldn't stay silent. I had been brought back for a reason, to warn, to guide, to help others find the same safety Jesus showed me. My life didn't just restart that day. It was reborn.